Hi, my name is James Walker, and I'm going to talk to you about my research with the development of experimental methods for active charge control using combined remote sensing methods. So, active charge control in this presentation refers to the use of one or more currents to influence the electrostatic potential of a spacecraft. So, ACC has actually been used in situ for decades. It started with the ATS 5 and 6 missions, where it was demonstrated that using electron emissions and plasma emissions, you're able to influence your own electrostatic potential through the emission of these particles. And then this work was expanded on and used in future missions such as the cluster missions, double star, and more recently MMS. It also led to the development of instruments specifically designed for controlling a spacecraft's electrostatic potential, such as the ASPOC mission. Now, each of these applications here and how it's been primarily used in situ in the past has been a controlled spacecraft controlling its own electrostatic potential, specifically to maintain a near neutral potential to offer the sensing of low energy plasma. Now, this project is instead going to be concerned with a servicing spacecraft controlling the electrostatic potential of a target. Now, this work is motivated by the electrostatic tractor research. So, the electrostatic tractor is a concept for geostationary debris removal. The idea is you have a servicing spacecraft equipped with a high energy electron gun. This servicing spacecraft approaches an uncontrolled geostationary debris object. The servicer irradiates the geostationary debris with the high energy electron gun. The increased flux of negative particles impacting the debris object causes it to charge very negative, while the emission of the negative particles from the servicer causes it to charge very positive. With these two opposing charges, you get an attractive force generated between the two. And it's this force that we refer to as the electrostatic tractor that allows the servicer to manipulate the motion of the debris object. And it was found in prior research that using the electrostatic tractor, a multi-ton debris object can be reorbited in a matter of months. Now, an important aspect of the electrostatic tractor research is being able to control the force generated between the two objects, which really means controlling the potential of each of the objects. And that's where this project comes in controlling the electrostatic potential of the uncontrolled target. Now we want to achieve this by using the controlled spacecraft to apply a current to the uncontrolled target. So in these experiments, we're going to be doing vacuum chamber experiments. So vacuum chamber conditions, the only currents acting on the target are going to be the electron beam and then the subsequent secondary electron current and backscatter electron current generated by the impacting electron beam electrons. Now, looking at these currents and how they're going to play into the charging behavior of the target, you can see that there are two variables that we can actually control. And that's going to be the current of the electron beam, IEB, and the energy of the electron beam, EEB. These are two values that we can control with the electron gun, so that's actually where we're going to apply our control. Previous work looked at applying control to the current of the electron beam, and that is what is shown here. We were able to achieve our desired potential by just applying control to the electron beam current. However, this work is going to deal with actually applying the control to the electron beam energy. We determine that's an easier and more effective control. So in this project, we're going to be applying a linear proportional controller to the electron beam energy to control the potential of the target. In the plot I just showed you with the active charge control, those experiments were conducted using an electrostatic voltmeter to measure the target's potential. This means that we were able to get about 1 second measurements, but an electrostatic voltmeter is not practical for in situ use because it requires a 3 millimeter separation distance, and that's just not realistic. So the AVS lab has actually explored remote sensing techniques in order to measure a target's electrostatic potential. And we've developed two methods. The first is the X-ray method, and the second is the secondary electron method. So when a servicer irradiates a target with a high energy electron gun, it's going to generate X-rays and secondaries. By measuring the energy of these particles and knowing the energy of the electron gun and the potential of the servicer, you can actually compute the potential of the target based on these values. So as long as we can measure the energy of the X-rays and or the energy of the secondaries, and we have knowledge of ourself, we can measure the potential of the target. For these experiments, we are incorporating remote sensing techniques into our active charge control. And in previous work, we found that the secondary electron method would be the better method to incorporate into active charge control, because while it is slower than the X-ray method, it has a 10-volt accuracy, while the X-ray method has a much lower accuracy. So we incorporate the secondary electron method into our active charge control techniques. So this work was still also previous research. We found that there are two methods for incorporating the secondary electron method into our active charge control. The first is a constant voltage sweep. So our secondary electron method uses an RPA to measure the energy of electrons emitted from the target based on the electron beam irradiation. And because we're using an RPA, we have to perform a voltage sweep across the grids of the RPA. So the first technique that we looked at was using a constant voltage sweep. So we start with our target's actual potential. We irradiate the target and we conduct a voltage sweep on the RPA from across the entire experimental space. So in this case, 0 to 5,000 volts with our small step size of 50 volts. And after one voltage sweep, we get our measurement of 1,500 volts with our 50-volt error. That is the first method. The second method that we looked at was a dynamic voltage sweep. So with the constant voltage sweep, you have a large state space, you have a large voltage step, you can end up with very large measurement times. The goal of the dynamic voltage sweep is to have quicker measurement times. So you start with your actual potential, you do a very unrefined sweep across the entire state space, in this case with a step size of 500 volts. You get your unrefined measurement, and then you perform a second voltage sweep based on that unrefined measurement with a smaller step size. And then you continue performing these more and more refined sweeps until you end up with your final refined sweep with your desired step size. And in this case, we get our 15-volt measurement with our 50-volt error. So incorporating these two techniques into our active charge control, we found the constant voltage sweep is able to accurately measure the target's electrostatic potential for a variety of gains. We see the behavior that with gains less than 1, we get an overdamped response. Where we have gains greater than 1, we end up getting an underdamped response. But in each of the cases, the control is able to converge to our desired negative 3,000-volt potential. Take note that it takes about 500 seconds or more to get confident convergence in this control. Now, comparing to the dynamic method, the dynamic voltage sweep, we start with our initial unrefined sweep with our 500 voltage step. Once we reach our 3,000-volt potential, we conduct a more refined sweep with a smaller step size. Once we measure 3,000 volts again, we do our final more refined sweep with our small step size, and then we converge to our desired potential. Now here you can see, even with the multiple voltage steps, we ended up converging much quicker in about half the time that it takes for the constant method to converge, and we get the same level of accuracy in the end. So from this, we can see that the dynamic voltage sweep is much quicker than the constant voltage sweep. However, we also want to look at how both of these controls behave in a changing space environment, because that is what we would realistically see in situ. So in this case, we are going to simulate a spacecraft coming out of eclipse, and that's going to entail, we're going to let our control converge to our desired potential with just the electron gun. We're going to then apply a photoelectron current, which is going to charge the target more positive, and then see how the control is able to handle that. So first, starting with the constant voltage sweep, you're able to see that we allow our control to converge, we apply our photoelectron current, and then the control just immediately measures the higher potential, and then adjust the control accordingly, and is able to converge back down to our desired negative 3,000-volt potential. The dynamic voltage sweep is another story. Once we converge to our desired potential, we're at this refined voltage sweep, which is just plus or minus 100 volts around our goal potential with our step size of 50. So in this case, the most positive potential we can measure is 2,900 volts, negative 2,900 volts. So when the photoelectron current is applied and the potential jumps up to near 1,000, we actually can't get an accurate measurement. We can only get this inaccurate measurement based on the voltage sweep. And this continues throughout the entire rest of the trial until we're actually able to drive the potential back to a value that can be accurately measured. So here we see that the dynamic voltage sweep is not able to accurately handle a changing environment. However, even with this, these inaccurate and inefficient control, we can still drive the potential back to our desired value, which is very interesting. So we just showed our previous work with our active charge control remote sensing methods, and we showed that we have two separate methods, the constant and the dynamic voltage sweep, both of which have its benefits and drawbacks. So what the goal of this project is to essentially take both of those positives and none of the drawbacks. So we decided that the best way to do this would be to seed the secondary electron method in what we call the dual method. So we start with our actual potential. We take a measurement with the X-ray method. We get an unrefined measurement through the X-ray method, which measures the entire state space. And then we conduct a refined voltage sweep based on that X-ray measurement with our 50-volt step size. And then from that, we get our measured potential with our 50-volt error. And the idea here is because the X-ray method can measure the entire space that we're going to be working in, and far quicker than the constant voltage sweep, we can actually use that as our undefined measurement to get quicker measurements, but also across the entire space that we're working in, so that we can handle a dynamic environment better. This is a primarily experimental presentation, so these experiments were conducted in the Eclipse vacuum chamber at the ABF lab at CU Boulder. And you can see the experimental setup here with our X-ray detector, our RPA, and our electron gun. So first, we integrated this dual method into our active charge control. We performed a 500 voltage sweep, so minus 100 volts and plus 400 volts from our X-ray method value with a step size of 50 volts. And the results we see are very similar to what we saw with the previous methods, where gains less than 1 are showing overdamped behavior, gains greater than 1 are showing underdamped behavior. But in each of the scenarios, we are still able to converge to our desired 50-volt error. We also conducted these experiments with a 20-volt step size, and we see very similar behavior, albeit with the smaller error bounds in the end. Comparing these results to our constant voltage sweep, we see that the dual method converges much quicker. You actually interestingly see similar behavior from the two, just that the dual method is far quicker than the constant secondary electron method, converging in less than half the time. Comparing it to the dynamic voltage sweep, you can see that they converge in very similar amounts of time. So even though the dynamic voltage sweep is doing like 8 to 9 measurements for convergence, and the dual method is doing 3 to 4 measurements for convergence, they still converge in relatively similar amounts of time. So just straight up comparing these convergence times, you can see that the constant voltage sweep still taking 260 to 600 seconds per measurement, which results in taking 800 to 2400 seconds before the control converges. So we have very slow control. While comparing it to the dynamic and the dual method, you can see that even though they have different seconds per measurement and different required number of measurements before accurate convergence, they converge in very similar amounts of time. So with this dual method, we are still getting the quick control and quick convergence of the dynamic voltage sweep. Now we want to look at how these methods handle a changing environment. So simulating the exact same scenario with a spacecraft coming out of eclipse, you can see that the dual sensing method gives us very similar behavior as the constant sweep method, where once we apply our photoelectron current, the potential jumps up to a much more positive value. The control measures this much more positive value and applies the subsequent control, which then allows the potential of the target to be driven back to its goal potential in a much more efficient manner. And comparing this to the dynamic voltage sweep, you see what you saw before, where the dynamic voltage sweep cannot accurately measure these increased potentials that are outside its refined range. So you get very inaccurate measurements and very inefficient control, while the dual sensing method gives us the accurate measurements across the entire state space that we see with the constant voltage sweep. So we found that in this project, we were able to seed the secondary electron method with the X-ray method, and that resulted in quicker measurements over the entire sample space, which means that we get the quicker control of the dynamic voltage sweep while also getting measurements across the entire experimental space that we had with the constant voltage sweep, meaning we would be much more suited for a dynamic environment, effectively combining both of the positive aspects of the previous active charge control techniques. However, there are still concerns with the X-ray method. So at present, the X-ray method does require some important calibration. So for each scenario that we are testing, the X-ray method has to be calibrated separately. So specifically for when we were applying the photoelectron current, stimulating the spacecraft coming out of eclipse, you had to have separate calibration for with a photoelectron current and without a photoelectron current. And this isn't realistic for in situ applications. We really need to have a more generalized approach to using this X-ray method. So one of the ways that we can improve our current methods is to improve the X-ray method processing, allowing it to be far less reliable on its initial calibration, therefore making it more general to spacecraft and to space environments and charging situations. The other aspect that we're going to look at is using a different method to see the secondary electron method. So rather than using the X-ray method that is very dependent on its calibration, can we use another method to seed the secondary electron method that would be more robust to a dynamic environment? This work was funded by the DoD through the NDSEC Fellowship, and then also AFOSR has supplied general funding for the electrostatic tractor research. These are just some references from the presentation. If you have any questions about the project, please feel free to reach out. But if you don't, thank you for listening and thank you for your time.